theoretical groundwork of the quantum geometric tensor, or QGT, and scale adaptive metric holding. The quantum geometric tensor provides a self-contained description of spacetime, encapsulating both curvature and torsion effects at the quantum scale. Unlike traditional formulations of general relativity, where spacetime geometry is treated as a smooth classical background that must be modified through external terms such as the cosmological constant, QGT naturally integrates these effects within its fundamental structure. This eliminates the need for additional corrections, making spacetime an emergent consequence of quantum metric dynamics rather than a fixed backdrop requiring external modifications. This shift in perspective results in a scale-adaptive metric in which the concept of distance is not rigid, but is instead influenced by the underlying geometric structure of spacetime itself. The way metric holding occurs across different regions is dictated by quantum interactions, leading to the emergence of cosmic expansion and other large-scale phenomena as intrinsic properties of the metric rather than imposed behaviors. A fundamental consequence of the QGT framework is that it removes the need for the cosmological constant in Einstein's equations. In classical cosmology, the cosmological constant was introduced as an additional term to explain the acceleration of the universe's expansion. However, within the QGT framework, the metric itself evolves dynamically in response to quantum scale fluctuations, leading to a naturally expanding spacetime. Rather than requiring a separate force such as dark energy, the behavior attributed to the cosmological constant emerges from how quantum scale metric variations accumulate at macroscopic levels. The expansion of the universe is therefore not a phenomenon requiring external justification. It is an inherent consequence of the self-adaptive nature of spacetime within the QGT framework. This means that cosmic expansion is not an imposed effect, but rather an emergent property of how spacetime defines and holds distance at different scales. This also explains subtle variations in expansion rates, such as the Hubble tension, as different cosmic regions may exhibit slightly different metric adaptation behaviors due to quantum scale variations propagating across large distances. Axion-like dark matter, or ALDM, as a metric modifier rather than a gravitational source. In traditional dark matter models, axions or other exotic particles are treated as mass energy sources that interact gravitationally with surrounding matter. However, in the QGT framework, axion-like dark matter does not behave as a gravitational source in the classical sense. Instead, it interacts with the fundamental metric structure, influencing the way spacetime geometry adapts to different regions. Rather than forming localized gravitational wells, axions contribute to large-scale metric variations, affecting how spacetime holds distance across vast regions. This perspective redefines the role of dark matter. It is not simply an unseen gravitational mass, but an active participant in shaping how spacetime adapts at cosmological scales. This explains why gamma rays from GW 170817 experienced a 1.7-second delay. Their propagation speed was subtly altered by axion-induced metric variations over tens of millions of light-years. Hubble tension arises naturally in this framework, as the expansion rate is slightly different in different cosmic regions due to variations in metric adaptation. Gravitational lensing anomalies occur, not just due to unseen mass, but also due to subtle modifications in metric structure caused by axion interactions. Scale-adaptive metric holding distance as a contextual property of spacetime. A central realization of this framework is that distance is not a fixed, universal property of spacetime, but an emergent, scale-dependent feature influenced by quantum interactions. Unlike in classical relativity, where distances are determined by a static metric, QGT dictates that how distance is held varies dynamically across cosmic structures. This resolves several cosmological puzzles. Cosmic voids may exhibit different redshift behaviors than dense regions, as the metric adapts differently in low-density axion-rich environments. Light bending around massive structures may show small deviations from purely gravitational predictions, as metric adaptation contributes to lensing effects. Gamma-ray delays in different environments should exhibit regional variations, depending on how metric structure is altered by axion-QGT interactions. Since spacetime actively defines metric structure rather than passively following mass energy distributions, all observed effects attributed to dark matter, dark energy, and cosmic acceleration can now be understood as emergent consequences of scale-adaptive metric holding rather than requiring independent forces. Cosmic expansion as an inherent feature of quantum geometric tensor or QGT. By removing extrinsic factors, the QGT framework reveals that expansion is not something imposed onto the universe. It is a natural byproduct of how metric structure adapts to quantum fluctuations. Unlike in standard cosmology, where expansion is driven by an unknown force, here it arises because metric adaptation varies based on the quantum scale structure of spacetime. This variation propagates across large scales, leading to differential rates of expansion in different cosmic regions. The universe does not expand at a uniform rate, but in a way that depends on the underlying QGT structure. This provides a self-contained explanation for the universe's evolution. Cosmic acceleration is not caused by an external force, but is instead a natural outcome of how spacetime defines scale. Observable predictions and tests for QGT-driven metric adaptation. The removal of extrinsic factors and the adoption of QGT-based expansion lead to several testable observational predictions. First, gamma ray delays should be energy dependent. Since metric adaptation affects refractive index, gamma ray photons of different energies should experience slightly different propagation delays. Future gravitational wave events should show subtle variations in gamma ray arrival times depending on photon energy. Next, void galaxies should show redshift variability. Since metric adaptation varies across different cosmic structures, galaxies inside voids should exhibit slightly different redshift behaviors than those in dense cosmic filaments. This could explain anomalies in cosmic expansion measurements and provide a direct test for QGT-driven variations in metric holding. Additionally, lensing anomalies should be region-dependent. If metric adaptation is influenced by axion QGT interactions, gravitational lensing effects should deviate slightly in axion-rich regions. Strong gravitational lenses near cosmic filaments may show additional distortions beyond traditional predictions. Finally, Hubble tension as a natural outcome of metric adaptation. If expansion rates vary across cosmic structures due to QGT variations, different measurements of cosmic expansion should correlate with surrounding metric conditions. Supernova-based and quasar-based measurements should reveal systematic variations based on regional metric adaptation. Final summary: the QGT-based view of spacetime. The quantum geometric tensor governs metric adaptation, removing the need for a separate cosmological constant. Axion-like dark matter does not gravitationally collapse, but modifies metric structure, influencing how distance is defined across cosmic regions. Distance is a dynamic, context-dependent feature of spacetime, not a fixed universal quantity. Cosmic expansion, gamma ray delays, and Hubble tension emerge naturally from QGT-based metric variations, requiring no external forces. Observational signatures in gravitational lensing, redshift anomalies, and gamma ray propagation provide testable predictions for this framework. This presents a self-contained, testable theory of spacetime evolution based entirely on the intrinsic geometry of QGT, eliminating the need for extrinsic modifications such as dark energy.